So let's take a look at this pulley problem we have here. So in this given diagram, we have this block A sitting on this flat horizontal surface here. We have a cable that comes all the way through around this pulley, down around through this pulley, up to the ceiling here. So the pulley over here directs it down from a horizontal motion to a vertical motion, where we now have this weight over here, B, with a single pulley there, comes back up to a fixed point on the ceiling. So they tell us that the weight of A over here is 10 pounds. The weight of B is given to us as 20 pounds. And we have our initial velocity of block A at 2 feet per second moving to the right. So that tells us our direction of motion here. So we can tell that if block A moves in this direction, again, the thing I really like to do with these problems is actually go through the motion, pretend it's moving, visualize it. So if block A moves this way, we can visualize that block B, this weight here at B, is going to be moving down in this direction here. So we understand the direction of motion, how things are moving. And it also tells us that we have a coefficient of kinetic friction here, mu sub k, which is between block A and the surface here, of 0.2. Now they're asking us to find VA, the velocity of A, when A has moved a distance of 4 feet. So some red flags should be going up there. Say, okay, we know there's an initial velocity given to us. We're looking for a final velocity. We know it's starting from 0 point here as far as displacement goes to a final displacement of 4 feet. And at that 4 feet, we could also find the time, how long it takes to go there, and that may be important as we're looking at some of our equations of motion. So we're already kind of formulating a plan in our head. So we come down here. What are we thinking? So since both forces and velocities are involved, this problem requires both the equation of motion and kinematics. First thing we want to do with that is to draw the free body diagrams. So similar to what we did in the last section, we're taking the drawing out of free body diagrams for individual components, so block A and mass B. From there, we want to apply the equation of motion using dependent motion equations and derive relationships between A and B. So we need to figure out a way to relate A and B. And if we look at this physically, these are related through this cable going between both of them. So taking things a little bit further than last time, doing our free body diagrams. We're doing out our equations of motion based upon those free body diagrams, and from there we're then going to solve for what we're asking us to solve for, our velocity at A. So now that we've had that opportunity to look through the problem statement and the given diagram, get an idea of what's going on, how the blocks are moving over the pulley system, and what they're asking us to solve for, our next step is to create our setup page. So that's exactly what we do here. We write down all of our given information in one clear spot so we can reference back to it. Our weight of A, our weight of B, initial velocity of A, coefficient of friction between A and the surface there, and that we're solving for V sub A when A has moved a distance of 4 feet. So now that we have the setup page here, we want to be able to formulate a plan for how we're going to solve this. And we'll leave that right on the setup page as well. So we can always reference back to all this information, go through our steps along the way of how we're going to solve it, what our given information is, how it's moving, and what we're looking for. So establish coordinate system. If we're going to go with the standard XY. If we want our Y going down positive, now that we know that B is moving down, but we want a different coordinate system. Draw out our free body diagrams, and then take it a step further than we have before now, and do out our equations of motion based upon the information in our free body diagrams, and then do our some kinematics as well, relating velocities and positions and accelerations of our individual blocks to solve for this final velocity of A when it's reached this distance. So now that we have our setup page created, we have all the given information clearly labeled, we understand what's going on within the system itself, have a clear spot we can go back and get all of our given values and what we're looking to solve for, what we want to do now is start our solution. And to begin our solution, if we recall when we were going through the problem statement, we needed some way to relate block A and block B. Now physically the way that these are connected is through this cable here. So how can we relate the motion, position of block A and block B based upon this cable? Well, we do know one thing about this cable. Its total length doesn't change. So even as block A moves to the right here and block B moves down as given in the problem statement, we can see, well, this will shorten, but these will lengthen. So we need a relationship for all the parts of the cable here that are going to change. So we can see if we go from the center of the pulley down here at B up to the center of this fixed pulley here on the corner, you can see we have this distance S sub B. Now we can see there's 2 times S sub B right there. And we can also see now if we go from the center point of this fixed pulley here to A, we have this length S sub A. Now we can note that this length from here to here, from the ceiling to the center of this fixed pulley, doesn't ever change. So we're not going to worry about that. Same with this length going around this pulley. That's going to be constant the whole time. We're not going to worry about that. So total effective length of the cable, we're going to call that L. L is going to have the relationship of SA, this distance here, plus 2 times SB to give us L. Now, if we wanted to go not only to relate positions, but to relate velocities, what we want to do is take the first time derivative. So we go from position of velocity, first time derivative of S sub A becomes V sub A. First time derivative of S sub B becomes V sub B. First derivative here, with respect to time of a constant value L, is 0. So now we have a relationship between the velocity of the 2 objects. Next, if we recall, we're dealing with Newton's second law for the equations of motion based off a free body diagram. The right-hand side of Newton's second law is mass times acceleration. So we're going to need to have a relationship between the accelerations of block A and block B, and we can get that by taking the derivative of velocity to give us acceleration, or the second derivative of position. So the derivative of velocity, VA, becomes A sub A, VB becomes A sub B. We have 0 on the right-hand side. We can rearrange this to get equation 3 here. Acceleration of A is equal to negative 2 times the acceleration of B. Now, the question we need to answer next is, what coordinate system do we choose? Go the standard Cartesian XY, where we have X positive to the right, Y positive up, that we've done many times before, and that's kind of our default. But we want to note A sub B, we go back up here, positive going down, okay, A sub A, positive going to the left. So we do have the option here of choosing this coordinate system right here. So if A sub A is moving to the left, that'll be positive, and if A sub B is moving down, that's positive. But if we go back and kind of move through the system here, we see, okay, if I pull A to the left, and what this would give us as the positive X direction, then B is going to be moving up. It would be the negative Y direction there. So we haven't really eliminated a negative there, and we could go through this for a couple different coordinate systems and really decide, is it worth choosing a different coordinate system, sticking with a standard X positive right, Y positive up, or do we do something different? So as we go through and draw out our free body diagrams, I'll go over some of those options and we'll play it back to our given diagram and see how those relate to sign convention. So the next step in our solution is to begin our free body diagrams. We do want our free body diagrams for one of these problems. One of the things we want to do is do a separate free body diagram for each of the objects within our entire system. So within our system here for this pulley setup problem, we have block A and block B. Let's take a look at just block B first. Now, one thing that we can do is for each of these objects, we could establish a different coordinate system for each one, and then a different coordinate system for the system as a whole. So let's do that just to kind of show you how that plays out and how that's going to affect your sign convention and understanding the directions of motion. So for this one here, let's go with this coordinate system here, X positive to the right, Y positive going down. So with that there, the first thing we want to do is go back to our given diagram, which is great that we have our setup page so we can always reference back to that and take a look at what we have. And from that given diagram, throw this right here like this, what we want to do is come up with our free body diagram based off that. So pages don't quite fit, but you can still see A, B here. We're dealing with B. If we look back at B and we want to determine what forces are acting on B, well, we're going to have a tension force acting up, and we're going to have a weight force acting down, and technically it's going to be 2 times the tension in this cable here. So now that I was able to quickly reference back to my first setup page for that diagram to understand what the forces were acting on this object B, block B here, I could easily draw out my free body diagram. So 2 times the tension force going up and the weight force of the block going down here. We want to draw a kinetic diagram as well. Well, if it's moving down, we have this right here, the mass of A times the acceleration of A. F equals ma, there's the right-hand side of Newton's second law for our equation of motion. So for the equation of motion, just for block B on its own, we now have my free body diagram, my kinetic diagram. I can plug right into my equation of motion. I go to Newton's second law, summation of force equals mass times acceleration, applied to this specific problem for block B, where I'm dealing with only y direction. Separate that out, so just the y, summation of forces in the y direction is equal to mass times the acceleration in the y direction. What are the summation of my forces in the y direction? Go right back up to my free body diagram. I can plug those right in. I have weight of B, 2 times my tension force. But I want to pay attention to my coordinate system. I've chose y to be positive going down. So therefore, if y is positive going down, my weight force is positive, but my tension force is negative. So this is where sign convention is important here. Weight's going in the positive y direction, because we call y positive going down according to our coordinate system, and tension is going in the negative y direction. So there's a summation of forces on the left-hand side of Newton's second law. On the right-hand side over here, I have the mass of B times the acceleration of B. For my kinetic diagram over there, plug in my known values, go back to my first setup page. Okay, my weight of B was given to me as 20. Minus 2t is equal to my mass was given to me as 20 over here, divided by acceleration due to gravity over here. Sorry, my weight was given to me as 20, divided by the acceleration due to gravity will give me my mass of B, so 20 divided by 32.2, where I'm in the right units here, times my acceleration at B. So I look at this, we'll call this equation number 1. Look at this as one equation, 2 unknowns, tension and the acceleration of B. Which again is why we already went through, and now we know we have a relationship between our accelerations of block A and block B, so when we end up with these, we'll have a way to relate our equations of motion. So that's kind of going on in the back of my mind as I'm looking at this equation here with 2 unknowns and only one equation. So we completed our equation of motion for block B. So we're going to do the same exact thing now for block A. Now, the question we need to ask ourselves here is, what is the coordinate system we want to use for block A? Well, they tell us in the problem statement that block A is moving to the right. So if block A is moving to the right, it might make sense to keep that as the positive direction. Keep it positive in the direction of motion. So I go to choose my standard coordinate system here, where I'm calling positive x to the right, and we'll go with positive y up there. So this is my chosen coordinate system for block A. And we know this is different than the coordinate system that we chose for block B. So all of my equations of motion for A are going to be based upon that. But things to note is we want to make sure that we understand the direction of motion of the individual items and how sign convention relates to that. So it's something to keep in the back of our minds. So we look at block A. Again, we can reference back to our first setup page. What is our given diagram? What is acting on A? We can see, okay, well, I got this tension force over here. I know I got a friction force, a normal force, and a weight force all acting on this. So looking at this, I can go ahead and use that information to start drawing out my free body diagram for block A. See the cables causing a tension force here. I have a frictional force, which again, we recall, the frictional force opposes the direction of motion. We know the direction of motion is the right. We have a normal force pushing up from the surface that it's sitting on the block itself. We have a weight force acting down in our negative y direction. So we can see tension is positive based on our coordinate system that we chose. Frictional force is negative. Weight force is negative. Normal force is positive. But we understand the direction of motion and understand how that relates to our positive and negatives in our chosen coordinate system now. Then we draw our kinetic diagram over here. We know the direction of motion is the right. We have mass times acceleration of block A for our kinetic diagram, right side of Newton's second law. So from our free body and our kinetic diagrams, our next step is to write out our equations of motion for block A. So we've already done for block B, now we're doing for block A, and we can simply take Newton's second law, summation of forces in our y direction. We want to do each individual direction separately. We want to do it for our y direction and our x direction. Let's do the y direction first. It's pretty straightforward. Y direction, summation of force in the y direction is equal to mass times the acceleration in the y direction here. So we know our y direction, it isn't going to be moving. It's sitting on that surface. There's no direction, so this is equal to 0. So summation of forces is equal to 0 over here. So, and we can clearly see that, only acting in our x direction, not in our y direction from our kinetic diagram. Boom. So it simplifies this down. What are the forces acting in our y direction? Well, we have a positive, according to our coordinate system here, normal force, and a negative weight force. So normal force minus our weight force of A is equal to 0. Normal force is equal to our weight force of A. Well, our weight force of A is given to us as 10 pounds, and normal force is 10 pounds. This is fantastic because we know that for our x direction, that normal force is going to come into our frictional force here. So now we have a numeric value for that to plug in. So our next step is to go through here and take a look at the summation of forces in our x direction. So Newton's second law, summation of forces in x directions is equal to mass times our acceleration in the x direction here. Okay. What are our forces? We'll go right back to a free body diagram, take a look at our x direction. Okay, I have a positive tension force and I have a negative frictional force. So negative F plus T is equal to our right-hand side. Well, now we do have something acting in our positive x direction over here, which is MA. So do this out here, take a look at everything. How do we start plugging in from here? Well, we know our frictional force here is given to us by mu n. Mu sub k times n, when mu sub k was given to us as 0.2 in the problem statement. We just solve for our n over here, positive value of 10 pounds. You can plug that in. Plus our tension is equal to our weight force divided by acceleration due to gravity. And this is where our negative is going to come into play here, because acceleration due to gravity is going to be acting down. This is acting up. So our mass is based off of that there. 10 divided by 32.2 times our acceleration of A, 2t minus 2. So now 10 times 0.2 becomes 2, is t minus 2 is equal to our negative value over here of our weight force here, which is 10 divided by 32.2 times our A sub A. So this is where sign convention is important. And I put a little note down here to kind of go over that sign convention of why we have a negative on the right-hand side of our equation of motion in the x direction. Well, because everything looks positive. But that mass, if you recall, weight is equal to mass times acceleration due to gravity over here. So if we have our weight here and we want to get our mass, we take our weight, divide by gravity. Our weight's a negative value because it's going down. Our weight's acting down here. We chose we chose y to be positive up, so that gives us that negative sign. So when we do this over here, weight is equal to mass times gravity, we have that negative, which plays in right there. So now we've gone through for both block A and block B, done out our free body diagrams, established our equations of motion, and have two equations now towards the end of that we can utilize. What we want to do is take those equations from the equations of motion that we found for block A and block B and combine them together in order to get towards our final goal, which again, recall, is the velocity of block A at a certain point, a certain distance. So again, we still need to relate these, and the way that we can relate these is going back to where we looked at the total length of the chord, or S sub A and S sub B is there, and we were able to, from those equations, establish a relationship between acceleration of block A and the acceleration of block B. And from that, we can now start plugging into our equations of motion from A and B as well in order to relate them together. So we look at this here. We have this relationship here that we call 20 minus 2t is equal to our weight over acceleration of gravity, or our mass times acceleration of B. That equation 1. Then we have t minus 2 is equal to negative 10 over 32.2 times the acceleration of A. So these are our two equations of motion that we had for block A and for block B. And we can see, well, there we go. There's from block B, there's from block A. We have now an unknown t, an unknown A sub A, an unknown t, an unknown A sub B. So 1, 2, 3 unknowns, 2 equations. We need a third equation. So there's a couple different ways that we can do this. We can see the common variable between these two is t. We can solve for t, plug them into each other, plug it back into 1, and put into our relationship over here for A sub A and A sub B. Different ways that we could do this. We could create these simultaneous equations, solve them in a numeric solver. We can set them equal to each other once they're both solved for t. Multiple ways that we can do this. So what we're going to do here is we're going to put 3 into 2. So 3 is the relationship that A sub A is equal to negative 2 A sub B. So if we put that relationship into this equation here, this equation now becomes t minus 2 minus 10 over 32.2, our mass, times, well, we subbed this negative 2ab into there. Negative 2ab replaces our a sub a. Gives us a double negative there, which is kind of nice because it cancels out. Now we're not dealing with a negative after that. Rearrange, solve this for t. And what we have here now is t is equal to our 20 divided by 32.2 times the acceleration of b plus 2. Now this gives us a relationship relative to a sub b with t here that we can plug back into equation 1. So for t, we can plug this in here back into equation 1. So we do that there. We say 20 minus 2 times t, which is this relationship here, is equal to our weight divided by acceleration of gravity times acceleration of b. So now we can see one equation, one unknown. All we got to do now is solve all of this for a sub b. So as I said, there's multiple ways we could have done this. We could have solved both these two equations for t, set them equal to each other, and then use this relationship. Sometimes it's easier to do one than the other. Other times it's just a matter of personal preference on what makes more sense to solve these. So we did it this way. Kind of an ugly equation, but we can work with it. So we end up with this here. We can distribute our 2 through here, simplify things down. We do that there. 20 minus 40 over 32.2 times our a sub b minus 2 times 2 is 4 is equal to the right-hand side of the equation, 20 over 32.2 times a sub b over here. Reduce it down a little bit more. We can put that 4 back over here. Combine it with 20. Becomes 20 minus 4 is 16. Minus our 40 over 32.2 times a sub b. 16, sorry. Now that you can see what I'm doing here. 20 minus 4 is 16. Minus 40 over 32.2 times a sub b is equal to, right-hand side over here, 20 over 32.2 times our a sub b. Reduce this down a little bit further here. We end up saying, okay, I got an a sub b there, a sub b there. I can subtract this over. Negative 40 minus 20 is negative 60. So 16 is equal to 60 divided by 32.2 times a sub b. Solve this. Multiply this over on the other side. A sub b is then 8.58 feet per second squared. So this is another reason why I love the startup page. I'm not done. This is just one part of the solution in the step along the way, and it's easy to forget what we're actually solving for. So we reference back to our first page. I need velocity of A, not acceleration of B. So how do I get from there to plug back to find that velocity of A at a known distance? So we have that acceleration at B. We know we're looking for the velocity at A at a known distance. So first thing I do is let's relate the acceleration of B that we just solved for back to our acceleration at A. Pretty straightforward there. We have this equation here from equation 3 that we can use to solve for a sub A. So a sub A, we recall from that equation relationship there, is equal to negative 2 times a sub B. We have a value for a sub B, so negative 2 times 8.58 when we plug that in becomes a sub A equal to negative 17.16 units of feet per second squared. And again, because of the fact that I chose different coordinate systems for block A and block B and our system as a whole here, I like to do this here so I don't get confused. I understand what this means. This means the negative value here means the acceleration of A is moving to the right. So it doesn't hurt to do this for you, for the grader. As I said, there's multiple ways to solve it, multiple coordinate systems you could have chosen as a reference. Let us know what direction the motion is in for your own good as you're solving the problem and for your graders or anybody else who might be reading through your solutions. So this value for our acceleration A can now be plugged back to what we call equation 2, where we can solve for that tension. So we're just going back through all those equations and getting out numeric values for all those variables there. So if we have this tension equation here, tension minus 2 is equal to our mass, or our weight divided by gravity with that negative sign, times, now we'll plug in our value here, so acceleration at A of negative 17.16. We'll plug that in there. Tension is equal to 5.33 plus 2 when we do that. Solve that out. Our tension in the cable is going to be 7.33 pounds. So from that, how do we get velocity? Well, this brings us to our kinematic equation. So if we go back to our equation sheets, we can reference these here, and we can see, okay, what do I know? What am I looking for? How do I get there? Well, I know I have an initial velocity of block A given to me. I now have an acceleration of block A. I also have an initial and a final position for block A. The only thing I don't have is my final acceleration. So if I go back through with everything that I have and everything that I'm looking for, I can find that this is a best kinematic equation when I go through all my list of equations from that sheet that I posted for you guys. I choose this one. So here's my general form before I've plugged anything in. Here's the chosen coordinate system over here. So again, we think, okay, this right here is given in the problem statement. Let's move 4 feet. Starts at 0, moves to 4. This difference between those two is 4 feet. A sub A, well, just solve for that. Again, positive going to the right from this coordinate system that I'm choosing here. And I said over here this was negative. That meant it was going to the right. So even though it was negative in this coordinate that we chose system here, it's positive in this one. So this leads to a very important point. Yes, you can choose individual different coordinate systems for every block, every free body diagram along the way, and that's fine. There's nothing wrong with that. But if you choose to have them all different positives going different directions, you need to understand what that means with different coordinate systems. So moving to the right, according to our negative sign here, well, the right is positive chosen according to this coordinate system here, so therefore it's going to be a positive value here. So something to keep in mind, sometimes even though it saves you some time in individual steps to have different coordinate systems, it might get more confusing at the end, and maybe sticking with one coordinate system throughout the entire problem for every individual object may be beneficial. Personal preference though. So plug that in there for my acceleration today. Plug in my initial velocity. Again, moving to the right is positive. 2 was my initial given velocity there. Boom, 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 all plugged in, all positive. Only unknown is my velocity at A. Plug and chug, velocity at A is equal to 11.9 feet per second, and that positive means it's moving to the right. So that's our final answer for what they asked us to solve for in the problem statement.